Now we come to a new set of examples. That was the end of the business set. This is a set of big data in science, or more generally in research applications. Here is a slide from The Economist, which had a special issue in 2010, already out of date. And it first starts with the Sloan Digital Sky Survey, and it points out that it only got 140 terabytes of information. And the successor of the Sloan Digital Sky Survey, the Large Synoptic Survey Telescope, which will start in 2016, will get 140 terabytes every 5 days. So that is 28 terabytes a day. So that's obviously a big increase. And it also here is giving things we've already discussed, that Walmart handles 1 million transactions every hour, and its databases, which is actually smaller than the example of eBay. But remember, this is 2010. I'm sure Walmart's databases are much larger now. It says that 2.5 petabytes, but and then it points out this is very much larger than the amount of information in the Library of Congress. And it points out that even in 2010, and this is surely much larger now, Facebook had 40 billion photos. And that's another example, the human genome. That took 10 years to analyze the genome. The first time it was done in 2003, but now it can be achieved in 1 week. And soon it will be achievable in hours or days. So this is just pointing out that the devices and processes that produce data are just getting far more effective every day. Here is an example related to the genome, and it plots actually the cost per genome. And in 2012, the cost per genome is around $10,000. And it started off, of course, a long time ago as $100 million. Well, not so long ago. That was 2001. Another important feature of this graph is it compares the cost of getting a genome with the performance of computers, which is Moore's law. And you can see that starting in 2008, there was a dramatic decrease in the cost of genome sequencing compared to the reduction in cost of computing. And now that's over a factor of 100 difference, which points out a well-known remark that if you start asking how much computing it takes to process these genomes, the computing cost is getting more and more significant because the cost of getting the data is going down so much faster than the cost of computing. Here's a sort of number which you can estimate. If you had a world where everybody had their genome sequenced, say, every 2 years, which some people might think is a possible world of the future where genes are used, the genome of individual genomes are used for personalized medicine in a new approaches to health, that will get you 3 petabytes of data per day. Here's another slide about radiology or medical imagery. It says that you have almost 70 petabytes of data per year coming from medical imagery. So that's a very big number. And then it actually divides it between the various sources. And actually it points out that if you added cardiology, that will take the answer to over an exabyte. That's 1,000 petabytes. Another, I mean, these sound big, but actually the amount of data produced every year is actually measured not in exabytes, but in zettabytes, which is a zettabyte is 1 million petabytes. Here's an example which we will do in more detail later on as our first use case. It is the Large Hadron Collider, which has become important and newsworthy item because in July they announced the probable discovery of the Higgs. And in fact, most people think they have discovered the Higgs boson. When we say probable, for a scientific discovery to become accepted, it requires it be checked in various ways and things like that, because everything is, it is possible either to get false data or misinterpreted data and things like that. This particular discovery is pretty solid because essentially consistent results were got from two totally different experiments running at the same accelerator, but different experiments. They're called the CMS experiment, which if you look at the ring at the top, the ring on the top left, that's the actual LHC accelerator. That LHC accelerator is a tunnel which is 27 kilometers in length, and it's actually, I think, 300 feet below the ground. And you will see it marks on that uh, circle, circle, the various experiments: Alice, Atlas, CMS, LHCb, and the ones relevant for the Higgs are CMS and Atlas, which are uh, relatively, from this sort of crude level, relatively similar apparati, and they both saw the Higgs. So it's worth noting at the top right, that's an actual picture of the Atlas instrument with some actual people there. Note that the instrument is giant, which is sort of interesting because the particles it's studying are very small. Protons have a size of around 1 Fermi, which is 10 to the minus 13 centimeters. As well as this apparatus, the actual tunnel consists of magnets which bend the protons to keep them in shape so that they actually travel in a circle and properly accelerate to get to the energies when they can collide. So this is probably currently the largest science experiment that measured in terms of data. It has 15 petabytes of data from various types, and this data involves a lot of computing. It suggests here there are around 200,000 cores. Those cores are scattered over the world. There are some at CERN, that's the so-called Tier 0 facility. Then there are 7, well, at least for CMS, 7 Tier 1 facilities. Those are essentially situated in countries, like there is one in the USA, and then there are 50 Tier 2 facilities. Atlas has a similar arrangement, and Indiana University has an Atlas Tier 2 facility. So this is big science. I mean, this single instrument has a few experiments. Each experiment, CMS and Atlas have around 3,000 people on them. And so you have 3,000 people devoted to these single experiments, and they publish papers as a group. And those papers have been submitted announcing the discovery of the Higgs. So just to show you what a Higgs looks like, here is some actual data from Atlas. The fundamental technology here is actually simple. It is quite unsophisticated compared to maybe some of the ways that the data is analyzed actually at eBay and Google and things like that. What you do is you take the raw data. The raw data is passed through extremely sophisticated analysis, converted into information, cleaned up data, and then and that information is, again, we have this gray area as to what's information and what's knowledge, but we can say that the information is the set of particle. We take the raw data, which is energy deposited and charged particle detections and things like that, or so-called Cherenkov light, detecting the type of a particle, and then we convert that into a whole set of particle momenta and possibly particle types. Actually, I should go back to the previous slide. If we look at the middle of the middle of that page on the right, there is an actual picture of an event. The two protons emerge from the bottom corner and the top corner. They collide in the middle, and then these lines coming out, and the blue energy deposits, they represent what's produced in this event. And the types of events you want to look at, the Higgs particle events, they correspond to high disruptive events where the protons are torn apart, and those deposit a lot of energy and a lot of particles traveling perpendicular or transversely to those initial protons. Whereas the typical collision, the protons actually just graze off each other, and you just get a spray of particles in the directions of the original protons. But this is an extreme event, a candidate for a Higgs, and we will come back to looking at that later on.